A very good day to you all. A very good day to you all. A very good day to you all, and a warm welcome to the free webinar on vibration and isolation systems and seismic protection systems for buildings and machines, a collaborative effort between Structural Design Institute and GURB India. And to give you all a brief introduction about the Structural Design Institute. Structural Design Institute is more commonly known as SDI. And if this is your first time with us, SDI is an educational institution that has a lot in store for you. We specialize in engineering, covering areas such as design, construction, and software training. What sets us apart is our close affiliation with civil and structural engineering consultants, a name synonymous with excellence in the field, having worked on several iconic projects in Sri Lanka. At SDI, we are committed to the professional development of engineers, focusing on courses such as structural analysis and design, architectural modeling, and even some courses focused on specialist topics. So what sets us apart from other similar organizations is our exceptional faculty, as our educators are all practicing engineers with extensive real-world experience, some of whom are even renowned in academia. We also offer a set of publications, including Tall Building Guidelines for Sri Lanka and Construction Specifications for Tall Building in Sri Lanka, the Colombo Lotus Tower, and the Detailing Manual of Reinforced Concrete Structures, as you can see on the screen, with more to come. These books encapsulate our team's wealth of experience, diving deep into design and construction specifics. Today's webinar on vibration and isolation systems, seismic protection systems for buildings and machine, focuses on vibration, isolation, and seismic protection technologies for buildings and machines. This webinar will delve into key aspects such as the principles of vibration isolation, seismic protection systems, application for buildings and industrial machinery, international and Indian project references, and practical design considerations. And this will highlight how these innovative technologies improve structural performance, enhance operational reliability, reduce vibration and related issues to protect critical infrastructure against dynamic loads and seismic events. So to introduce the speaker for today we have from GURB India, Mr. Prateek Bagaria joining us. Mr. Prateek is a senior manager of projects at GURB India and specializes in vibration isolation, seismic protection, and noise control solutions for buildings, industrial facilities, and infrastructure projects. With over 15 years of experience in structural dynamics and engineering applications, he has worked extensively on vibration mitigation systems, base isolation, tuned mass dampers, floating floors, machine isolation, and structural damping technologies across diverse projects. Mr. Prateek holds a bachelor's degree in civil engineering from BIT Mestra and an MBA from IIM Kozhikode. So now, without taking much time, I would like to hand over the controls to Mr. Prateek Bagaria, warmly welcoming him as our resource person to conduct today's webinar. Over to you, sir.
Good afternoon, everyone. First of all, thank you so much, Andrea, for this introduction. And I would like to say this and put this on the table that I have traveled all around the world, but this happens to be my most pleasurable and beautiful trips because Sri Lanka is very beautiful. And I'm deeply honored to speak in front of Shiromal sir and Professor Mendes. They have invited me, and the topic for today, as Miss Andrea has already iterated, vibration isolation systems and seismic protection systems for buildings and machines. First, we will talk a little bit about buildings and structures and then a little bit about machines. Straight away jumping into the topic, what sort of vibrations can really disturb a building or a structure? What could be the different sources of vibrations that we will talk, and then what all different types of buildings and structures do we need to assess and will need some sort of a technological intervention to make them safer, and then we will talk about the solutions. So different sources of vibrations could be many, which can, you know, give any kind of a trouble to buildings. Rail is a major source of vibration. I don't know how much it is of an impact in Sri Lanka particularly, but rail traffic is a big concern in many countries. We know that, the metro lines, and there have been so many news articles about all of these issues where, buildings develop cracks and other issues happens to the regular uh, life cycle of the building when there is a metro going close by. So metro is really a troublesome thing when it comes to building, if the building is close by to the metro. Road traffic is also an issue. Again, there are many issues in buildings when the road traffic is very nearing to the building, and the vibrations can be a concern. The machineries, the giant machineries operating near the building can be a concern. And earthquake, the elephant in the room. Earthquake is always a concern. You can see this picture which I have taken myself. This is, the clock tower in Kathmandu. So earthquake is the major source of vibration for any structure if it is in high earthquake zone, and we all know it already. Wind can be a very important load case to be studied, and is of course, the one of the most detrimental sources of vibration when it comes to tall buildings or long spanning structures. So yeah, we will see some photos presentation, but this during the question answer session, I would like to start the question answer session myself when the presentation ends. And the question for today is, if you see all the poles are vibrating left and right, but one particular pole is not vibrating at all, which is this pole in front of the you know I would like to know why this pole is not vibrating. So just for your interest, I'm playing the video again. I would like to know why this one particular pole is not vibrating at all. It's not oscillating at all. Everything, just one pole is not oscillating. I mean, there can be many issues in the building. Wind happens to be one of the important things to be studied, along with several, and buildings can really face some detrimental troubles when it comes to wind. Pedestrian traffic for some kind of structures, long spanning structures, can be an issue if it is a long spanning floor, office floor, or a bridge. So all of this constitutes the different sources of vibrations when it comes to any sort of a vulnerability with regards to safety of the building. What kind of structures do we really need to study for vibrations? Not the regular residential buildings, but at least the residential buildings of some importance really need some assessment. Some big hotels, all the photographs that you see in my presentation happens to be our project photographs, and there can be some questions around the photographs also later when we conclude the presentation. This is Hotel Sheraton in Paris. It is all isolated by vibration isolation systems. So yes, hotels can be one kind of buildings which need some assessment because it houses a lot of people. Theaters, concert halls, cinemas, office buildings, hospital buildings, railway stations, the modern railway stations, the broadcasting stations these days, data centers and broadcasting stations, semiconductor facilities are coming up a lot, discotheques or whatever. Any facility or any building, if it is of some importance, needs some assessment, and all these different sources of vibrations which we just saw needs to be studied, particularly for these important buildings. Also, there is one more structural element which needs some assessment. Some facilities in the building which create vibration and disturbs the other parts of building also need some assessment. For example, you have helipads in building, or you have swimming pools in the buildings, auditoriums inside the buildings, banquet halls, gyms, recording studios, dance floors, acoustic rooms in some kind of a facilities, or the data center labs, the clean rooms and the biotechnological rooms, etc. Inside the high-end data centers and semiconductor facilities. So all of these facilities inside the building are also very vulnerable to vibrations or create a lot of vibrations themselves and disturb the other portions of the building. So these are the different facilities which need some assessment within a building. Some other kinds of structure also need some assessment. If it is a high-rise building, this is Dubai frame, where we have put tune mass dampers. So the high-rise buildings, the air traffic control towers, or the tall statues in the world, the chimneys of plants or whatever, wherever, the large and long spanning bridges around the world, the large cantilevers if you are building any. So all of these different kinds of structures which are not regular structures also needs assessment when it comes to study of vibrations and earthquakes, stadiums as well. Now, coming to the main topic, what is the solution for all of this? We already noticed what all different sources of vibrations can disturb, what all different kinds of buildings and structures. But what are the different solutions for this? First solution that comes to the mind of an structural engineer is to change the shape of the building. And he talks to the architect, but more often than not, it will not be allowed and it will not happen that you completely change the building itself. Then the structural engineer decides to increase the structural stiffness by adding more and more mass, going the old conventional way, going into the 1500s and 1600s, where you just dump mass and make the structure heavy. That's also not possible in most of the cases these days because of several reasons. You already know it. So what do you really do? What you do is, depending upon the class, size, geometry, use category of the building, and so many other factors, either you isolate the building or you increase something called as damping in the building. Now, to do all of this, to either isolate the building or to increase damping into the building, first is you can isolate the building. Again, as I said, depending upon the size, geometry type, class, importance category, occupancy category, etc., etc., the solution will be decided. But essentially, these are the solutions. The building can be isolated at the bottom, or there can be supplementary damping offered to the building in form of small dampers put along the height of the building. As you can see, viscous wall dampers, number 2. Or you can put a concentrated damper at the top of the building if the building happens to be a high-rise building, and control the vibrations due to wind. Also, as I said, for helipads and other things, you have something called as floating floor. Or you can isolate the equipments or the machines inside the building using the same concept. So essentially, these are the things that we will be talking about today, which is isolating the building at the bottom, increasing the damping of the building all through the height of the building by introducing something called as small dampers, supplementary dampers, or viscous wall dampers, or putting up a concentrated form of a damper called tune mass damper at the top, and floating floor, as I said. So first we will talk about isolating the building. To cater to this vibration challenges, we can isolate the buildings using two different types of solutions. First is low frequency isolation systems. These are three-dimensional isolation systems made of high performance springs, helical steel springs, along with something called as dampers. It may be needed for some earthquake or some other purposes, which we will talk about later. But steel spring systems assisted with something called as dampers. And this overall technology happens to be the best in class technology available for isolating the building because it gives highest of the performance, and this offers something called as three-dimensional mitigation, not just translational mitigation, which is left, right, front, and back, but also up and down, the vertical mitigation as well. And you achieve lowest of the frequencies. That's why this happens to be best in class. The second option that you have is using closed cell polyurethane bearings, which is called Novo Damp. And these are medium frequency isolation systems, more than 6 hertz solutions. These are usually cost effective. And this happens to be something called as good to have solutions, because this is something which is essentially you should be using if you are dealing with any vibration challenge. But if you want the best in class solution, you have spring systems. Again, there is a disclaimer that something called as resonance is to be avoided and frequency plays a major role. So frequency is the deciding factor, but in general, these are the two options that you have to put in an isolation system to control the vibrations entering the building, or when you are deciding to make a floating floor, again, same things. This is an animated video. You will see how a base isolation system, we call it base control system, essentially works. So if you have an independent building or any facility, even a machine for that matter, and because of an earthquake event, when there is no isolator, the entire facility shakes. But if you have the steel spring systems and the visco damper in combination put underneath the building, then what happens is the combo of the steel spring system and the visco damper absorbs all the vibration from beneath, whatever vibrations because of earthquake or because of rail movement, traffic movement, or whatever tries to enter the building, it all gets absorbed at the bottom, like how you are seeing in the animation video. And the spring moves, the damper restricts the movement and controls the oscillation. And that's how the vibration is stopped from entering into the building. So basically, it acts like a filter, and the vibration is essentially filtered. Now, just a small case study I would like to present, which we did with Mendoza campus of National Technology University of Argentina. For several months, we had deployed our accelerometers and other measuring instruments in the building, one of which had rigid base and another had our base control systems. And we measured the actual accelerations in both the buildings during a live earthquake, and these are the results. Let's not go very deep into analyzing all of the results, but let's say we see just the base shear. If you see the base shear at the bottom left corner of your screen, comparison of the total base shear of the two buildings, the thin line showcases the base shear of the building which is not having any isolator. And the thick bold line showcases the base shear of the building which has base control system. You see, the difference is multifold. So you can understand that the reduction in forces, in acceleration, in displacement, drift velocity, all these performance parameters is huge. After deploying the base control systems, the internal forces in the building and all these performance parameters, what I just mentioned, gets much reduced. So much so that the relative displacement in the building also is, as you see, the interstory drift between the base control system building, the building that has base control system, and the rigid body motion curves is very, very small. This is an example project. This is a very new ultra luxury hotel project in Mumbai, in India, just outside the Terminal 2. It is called Shrem Fairmont Hotel. There is to be a metro line coming up in front of the hotel, which will come up in few years' time. And for that reason, the client wanted the building to be isolated. Of course, we can also isolate the track. We can also isolate the metro, which we will be doing, which we do. And it is quite possible. But who knows if the metro authority will really isolate or not isolate in the future. So the choice was made by the client, and the building was supposed to be isolated using the isolators. About 180,000 tons of dead load, 180,000 tons of dead load was supported on the steel spring systems and the visco dampers. It is in operations now. The hotel is open for guests, but the entire hotel happens to sit on these springs and the visco dampers, controlling the and absorbing the vibrations from outside entering into the building. Acts like a filter, as I said. This is Hakata railway station, Japan, which was extended from one portion to the entire stretch, covering the air concourse over the platform. And the vibrations from the rail should not be entering the new yellow color extension of the building. That was the idea. And again, the isolators were put to do that. This is a concert hall in UK, which happens to be very close to the metro line, overgrade metro line. And in UK, in concert halls, they play something called as opera, if I'm pronouncing it right. So even minute levels of vibration and noise can be very disturbing for the uh, uh, whoever plays the opera. So this building was again isolated using the vibration isolators, the base control systems, along with dampers, as you can see in the photographs on the right. And the level of isolation, if you see, is not very straight, because it is decided on the basis of importance. Like, you would not want to isolate the basement because it is not carrying anything very important, and as the load increases, the price of the isolator will increase, etc., etc. So yeah, so the level of isolation is decided that way. And it's not something that GERB has been doing very recently. These are very, very old buildings in London, which you can see a train going through and through the building, and the building is sitting on springs. This again, it happens to be about a 45-year-old project for us. The entire residential complex sits on springs. It's in Germany. The springs, as you see, is integrated along with the visco damper inside the same unit. This is Glacier office building in France. And now I would like to show you the closed cell polyurethane case study, which is, as I said, good to have solution, the high frequency solution, which is made of closed cell polyurethane called Novodamp. So this is India's first airport-like railway station. This is called Habibganj, or recently the name of the station is changed to Rani Kamlapati railway station. So this station has a concourse which spans from one side of the station to the other side of the station. It is quite huge in terms of area. It is about 54,000 square feet. And the entire concourse sits on Novodam pads, the polymer pads. It is very, very simple and sleek, about 30-40 mm in thickness. Usually what we make is something in the multiples of 12.5. So this particularly was 37.5 mm in thickness, the pad, and the sizes depends on the load, the grade of the Novodamp or the type of the Novodamp also depends upon the load. So about 300 mm by 300 mm, let's say 37.5 mm thick, just like a slab, just like your notebook, and that's all. Controls all the vibrations that originates from the movement of the train and goes into the concourse area. Now these concourses will be used for sleeping pods, restaurants, high-end offices, etc., and you would not want any disturbance inside the concourse area. Now India is also planning to develop residential facilities over the concourse and over the railway stations, where such solutions can really prove very beneficial. Now we talked about isolating the structure and uh, creating this filter using two technologies. One is base control system and another is closed cell polyurethane. But depending upon, as I said, depending upon the type of the building, the use case, etc., you can also increase the damping in the building. Now, to increase the damping in the building, you can add supplementary dampers. Now, if you don't add a supplementary damper or you don't do anything, you know how the seismic response of a conventional building would be. I will not go into that. But if you use a supplementary damper, this is how the seismic response of a building with a supplementary damper would look like. Once the damping of the building is increased, the base shear displacement drift, just shift it to the corner. Once the damping of the building is increased, the base shear displacement, drift, acceleration, velocity, all these parameters will come down, simply because you have increased the damping. And this is something very easily correlated and established by different codes. Of course, Indian code, but so many other codes as well. In Eurocode, in ASCE, or in IEEE, whatever. If you see exactly at 5% damping, which usually people consider for, as per code, for their RCC building design, for 5% damping, the correction factor is 1. This means you do nothing. You change nothing, there is no change because the factor is 1. But if you increase the damping from 5% to, let us say, 10%, you see there is a correction factor of about 0.8. Now, what does it mean? It means that you can multiply this correction factor in your application of force of earthquake. When you are applying the earthquake force, you can multiply this correction factor of 0.8. That means you can reduce the application of earthquake force by 20%. Why are you able to reduce the application of earthquake force by 20%? Because you are able to increase the damping from 5% to 10%, which essentially means that the building is now more resilient. The building has now more damping to be able to take into account the earthquake forces. And for that reason, the code allows us to reduce the application of the force itself at the first place. And as I said, this is very well documented in many codes, many guidelines. This is one reference from the Indian code, where again the damping percentage and the factor, in some codes it is mentioned as a multiplication factor or a multiplying factor. In some codes it is mentioned as a correction factor. But for 10% it is 0.8 and it goes up to 30%. The damping can go up to 30% and you can take the benefit up to 0.5, meaning you can reduce the application of earthquake force by 50% if you are able to increase the damping from 5% to 30%. And how do you increase the damping? Is by adding viscous wall dampers, is by adding the supplementary dampers into the building. And again, as I said, these things are very clearly mentioned in all different kinds of global books or codes, whether it is ASCE or California Building Code or the UBC or the Europe Code, etc. So in FEMA also. And there are enough research papers from our office, from several other places on this particular subject. Now, what essentially this viscous wall damper looks like, or what exactly is the viscous wall damper? If I go back, for base control system, it was a spring system with a pot damper on the side of the spring system, creating a filter for the vibration not to be going inside the building. Here, viscous wall damper acts like a resilient system which is added to the building, offering extra damping into the building. It is a very sleek, maybe 60, 70, 80 mm thick tank, has a bottom body, has a bottom tank, as you can see in the picture, and a top plate called piston, which goes inside the tank. The black portion of the image that you are seeing on the right is the piston which goes inside the tank. And the tank has something called as viscous mass. Now, when there is an earthquake event, the earthquake force that goes into the building gets consumed in moving the piston inside the tank, inside the damper. And since there is viscous mass, the energy that the earthquake forces generate inside the building gets consumed in moving the piston inside the tank within the viscous mass. That's how the energy dissipation occurs and the earthquake forces gets absorbed. To do the analysis with viscous wall dampers, you have to perform, I'm sure you all know it, nonlinear time history analysis, and the modeling part of it, which involves exponential Maxwell damper model, and you need to model the links, etc. You can reach out to us for any help if it is needed to model the dampers into the building, and to do the time history analysis as well, or whatever is needed with regards to viscous wall dampers to be integrated into the building. But yeah, essentially analyzing your building with viscous wall dampers and checking its performance vis-a-vis your building when there is no viscous wall dampers, it is not a big giant of a task. It is something which we can do it in a week's time and establish the efficacy of the dampers. Some project examples I will run through quickly. This is Hotel Intercontinental in Sofia, Bulgaria. Viscous wall dampers are installed to take care of the earthquake forces. But this is a retrofit project in which the building was extended from 3 stories to 5 stories. And you see, without the viscous wall dampers, the displacements were so huge, the cyan or the green color line. And with the viscous wall dampers, the displacements have come down to absolute allowable limits. And same thing goes for base shear. This is a data center project for which we did the analysis comparing the building with viscous wall dampers vis-a-vis building without viscous wall dampers. Again, this is a commercial building which was getting converted into a data center. And if you see, from 5% damping across many different nonlinear time history analysis, we could increase the damping from 5% to an average of 30%. And the base shear was reduced, as was expected as per the codal values, that if you increase the damping to 30%, the base shear should reduce by 50%. And this is the proof that the base shear really got reduced by 50% when we added when we established 30% damping. Same thing for the interstory drift with and without damper. And also the acceleration, you see a peak in acceleration here in the right hand side image in your screen. This is in the y direction because we suddenly have stopped the damper. in one of the rows. So that for that reason, there is a peak, but still it is within the limits. Again, this is a project of a luxury apartment come hotel in Kathmandu, very high seismic zone. Between the blocks, the seismic gap was to be reduced, and with viscous wall dampers, as you know, the drift displacements can be controlled. Modeling the viscous wall dampers and the appropriate locations, we could increase the damping from about 5% to about 9%, and which gave us good results in reducing the displacement to the acceptable limits. And the pace shears were also reduced uh, as an effect of it, which was not a requirement, by the way. So this is just one image with one damper, but there were, I think, 85 dampers in this project, which were put at many locations inside the building. This is Bone and Joint Hospital in Srinagar, where we have installed again many viscous wall dampers to take care of the earthquake loads. Now, these viscous wall dampers are connected with bracing style of connection. Usually, for bigger dampers, we put we connect it directly with some auxiliary steel at the top and bottom. If the damper is pretty small, we go by such bracing kind of a mechanism. This happens to be a building project in Mexico that we recently did. Here, again, viscous wall dampers are put inside the building, eliminating all the shear walls, and not in the periphery, but within and inside the building framework. As you can see in this image, there is viscous wall dampers eliminating the shear wall locations. This is a 300-bedded district hospital in Sikkim in India. Many viscous wall dampers again here. As I said, the auxiliary steel at the top and bottom are usually put if the damper is big. This is for a project in Thailand where for wind, not for earthquake, but for wind, viscous wall dampers are put. It can be the viscous wall damper can have one piston inside it, or it can have multiple pistons inside it. If we have more pistons inside it, it can generate more resistance, it can generate more damping, and thereby take care of more and more earthquake forces. So we can make viscous wall dampers with a single piston, single vane, or maybe with double or triple vanes or pistons. Some actual pictures of the viscous wall damper from the manufacturing facility. The two connection schemes that I talked to you about. These are some testing photographs of the viscous wall dampers, and this is how the viscous, just to show you during a test how the viscous wall damper moves and how it is tested. This is the test setup of the viscous wall dampers. We have collaborations with many universities around the world for testing of the viscous wall dampers. We also have collaboration with a university in India, in Jaipur. So we can test the dampers if needed in India as well. For retrofitting projects, the dampers, or even for new projects, the dampers are supposed to be in the framed structure. The structure needs to be framed. So this is how the damper comes and gets positioned between the beams and the frame. There are many viscous wall damper projects around the world. It is not something very new. Maybe, it has been in existence since last 40, 50 years or so. So from US, in Japan, of course, many projects, the Docomo building in Tokyo, famous Docomo building, in Waseda University, or some other buildings in Japan. So these are very, very old images of viscous wall dampers around the world. If you see, this looks also very old. Now, few merits of viscous wall dampers when it comes to a solution which can really help the building to control the earthquake forces. These are completely passive systems. There is no seal, there is no valve, there is no orifice, there is no possibility of any failure. And these are also fix and forget systems. These don't require any maintenance or anything of that sort. You get the cost benefit in many ways, which we can figure out when we use the system. And you get the architectural comfort in this fashion that, since the viscous wall damper works on the principle of interstory drift, the story drift happens to be same across all the bays. So you can shift the damper from one bay to other bay and you really have the same result. So that's the way you get some architectural comfort. And also, since you are able to essentially reduce the beam and column sizes, I'm sure the architects will be happy listening to that. Uh, on the right hand side, the graph that you see is very informative in many ways. Let's say the cost of the building is 100 million without the damper, the blue line, at the start of the project, at the start of the building. And then cumulative cost of the building, the blue line, increases from 100 million to 110 million over a span of 10 years. Versus the building with damper started at 102 million and reached up to 112 million after 10 years. And after 10 years, what happens is there is an earthquake event. Now, the building that did not have the damper, which which had cost me 110 million up till now, will be in a very, very bad state. And you will need a lot of money to reinstate the building, to take care of the building in many ways, to do all the rehabilitation, to do all the corrective measures, etc. But the building that has damper, you would hardly need to invest that much of money again to make the building live again. Just a small, corrections here and there, retrofitting here and there, and you are sorted. So that's the benefit of having dampers in the building. If an earthquake hits, the building with dampers really can save you on cost as well, major cost as well. Now, let's go to the top of the building. If the building is quite tall, which happens to be now the case worldwide, and of course in Sri Lanka also we are seeing many tall buildings coming up. So tune mass damper is that technology which can help tall buildings take care of the high vibration amplitudes which arises due to wind or earthquake. We know that tall structures gets easily excited because of high vibration amplitudes, and we know that uh, because of vortex shedding, the buildings can vibrate, and not just vibrate in several different modes, and many modes could be vulnerable, not just one or first or second mode. So that's the reason for tall buildings, vibration assessment, damping assessment, and you do wind tunnel and you do so many other activities, but then damping is something which is critical. So these are some just to show you the effects of wind and earthquake in tall buildings, whether it is a building itself, the facilities inside the building, the pool inside the building, the partition inside the building, everything goes for a toss. We know already that many buildings in China or even in the US are facing leaks, creaks, breaks, etc., and are unoccupied completely because of such issues, and often asked to be vacated. So again, what do you do during design? Again, as we discussed in the very beginning, either you can change the shape and the geometry of the building, which will be very difficult, or increase the stiffness or mass of the building, which may not be economical or may not be suitable because you really cannot change the shape and geometry again. Increasing the stiffness and mass also will be difficult. So what you do is you add supplementary damping into the building by adding a tune mass dampers. I hope that you already know what tune mass damper is, but just very briefly, it absorbs the extra kinetic energy that is getting generated into the building because of the excitations coming from wind or earthquake, and it sets itself into motion in the opposite direction. when it sets itself into motion in the opposite direction, it essentially absorbs the extra kinetic energy that is trying to disturb the building. What really happens is when you add a tune mass damper into the building, as the name of tune mass damper suggests, tuned mass and damper. There is a mass which is tuned to the frequency of the most vulnerable mode of the building, meaning it is having similar or near same frequency as the most vulnerable mode of the building. And that's why it, it is able to absorb the energy and sets itself into motion out of phase to the structure and reduces the amplitude substantially across the frequency bands, essentially the resonating band. So that's the main part. And if you see the free vibration decay curve also, the absorption of the kinetic energy is not just the only part. What happens is it absorbs the energy very fast, and also the absorption is pretty high, meaning the vibration amplitude is not just subsided, it is subsided very fast and it is subsided a lot. Now, if you see this particular graph, which is from a journal from Orup, it was researched and presented in 2008. Damping ratio plays a very, very important part. Now, for tall structures, as per several codes, you consider a damping ratio of 2%, I believe. But if you see, all of your structures, mainly whatever you design around 100 meters, 200 meters, even less than 100 meters, 80 to 90% of your structures happens to be below 2% damping. And these are all actual damping values measured by the authors of this journal. So if you see, the damping is not even 2%, which you have been, assuming in your calculations. So what really happens if the damping is not 2%? This happens. Acceleration is inversely proportional to square root of damping. So if the damping is reduced in actual, if the damping is not 2%, on the x-axis, if you see, if the damping happens to be less than 2%, say 1%, then the acceleration shoots up like anything. The acceleration increases like anything. So what happens is, if the damping you have assumed is less and not 2%, the building oscillates more. And as per Orup's study here, hardly any building displays in actual the 2% damping which you have assumed. So what we recommend is, when you are designing your building, first of all, you should be very, very careful about assuming the damping ratio. If you have done a wind tunnel study, or if you have talked to the experts, if it should be 2% or less, maybe 1.5, maybe 1, or whatever, you should be particular about the damping ratio that you have chosen, one. And second, we recommend that you add one extra mass at the top of your building, say about 1% of the mass as a contingent load on the top. Why? Because during the completion of your building, if you are able to measure the damping and you register that the damping is not 2% or damping is not actually what you have assumed, then your accelerations will shoot up and you will need to do something about that. And that time you would probably need to retrofit a tune mass damper, which usually is heavy. So how do you add that weight on the top of your structure? So to add that weight, if you already have tolerance and if you already have taken that as a contingency load in your design by adding 1%, so usually the weight of the tune mass damper is 2% to 5-6% of the modal mass of the most vulnerable mode. Now, the most vulnerable mode modal mass would be usually 50-60%. Now, if you see 50% is the modal mass and 2% is the weight of the TMD. So the overall weight of the TMD as per the total weight of the building becomes 1%. So minimum 1% weight extra you should be adding at the top. That's what we recommend. As I have already said, tune mass damper, as the name suggests, has something called as a damper, and it has a mass which is, related to the most vulnerable mode in terms of weight. And you have a tuning component which can be either pendulum ropes, rail systems, springs, or whatever, to move the mass and set it up at a particular frequency, which happens to be a frequency close enough to the frequency of the most vulnerable mode. Now, this is one animation video where you can see a building vibrating when it is having absolutely no assistance of external damper versus a building which has a TMD. Now, if you carefully see on the left, the building is going, let's say, left. On the right, the building is the damper was moving opposite. So the damper moves opposite to the motion of the building, and this is how damper operates. The mass which swings or moves in the opposite direction and has its control over oscillations through dampers. Some project examples just for you to relate.
The statue houses two 200-ton suspended tuned mass dampers to make it stable enough to withstand violent winds plus seismic activity.
World's tallest statue, called Statue of Unity in Gujarat in India. This houses two 240 tons tune mass dampers. It is mentioned 200, but it is essentially 240 tons each. So two 240 tons tune mass dampers at the chest level of the statue. There is an observatory deck, and these dampers are positioned there to take care of the wind vibrations. Again, many such examples. This is DC Tower in Vienna, 300 tons of tune mass dampers right at the top of the building. This is the very famous hotel Burj Al Arab in Dubai. And as I said in the beginning of the tune mass damper portion, that there can be several modes which can be vulnerable in a building, not just the mode 1 or 2. So here, if you see, the exoskeleton of the building has many tune mass dampers, 11 tune mass dampers taking care of different modes of the building. And the tuning element need not necessarily always be the pendulum ropes. It can be springs, as I said, it can be rail systems, etc. So this is one such example where pendulum ropes are not used, but spring systems were used. The damper, again, the dead mass of the damper can be formed in any which way or any shape or size as we would like. So this is a ring type tune mass damper inside the Bay Bridge Tower in China. This is again a simple pendulum tune mass damper in ATC Tower in Scotland. This is a double pendulum tune mass damper to take care of two different types of frequencies all at once inside the hotel, 318-meter Aspire Tower in Doha. And this is a very interesting project, Madison Square Park in New York. If you see the bottom portion of the building, you will be amazed to see what you are seeing here. The building is not going right from the bottom to the top in a squarish or a rectangular manner. It is cut at the bottom, maybe because these guys were not ready to give the land. I'll also show the video of the tune mass damper that is put over the top in this building. This is air traffic control tower in New Delhi in India. This is the Orbit Tower, London in United Kingdom. Again, you can see how complicated the structures are, but then tune mass dampers are something which can help these structures. Essentially, the building's shape does not matter. What matters is the modal mass, modal shape. So if the damper cannot be housed inside the building, it can also be, let's say around the building, as you're seeing here. In all other cases that I showed you, the building housed the tune mass damper, or the tune mass damper was inside the building. In this case, the building is inside the tune mass damper in a certain way. Similarly, the ring type tune mass dampers are done for tall chimneys, which are vulnerable for wind. Now, this interesting one. This is a steel chimney in a power plant in Rwanda. If you see again, one chimney, but one is not. Very similar to the first video that I showed you, which we will be discussing later. So here we designed the tune mass damper, put everything inside a container, and the containers were shipped, and the tune mass dampers were put on the top. Nobody from our office or our factory visited this site. Just a small measurement machine was sent. It recorded all the vibration data. The data was sent across, and we could design the tune mass dampers, dispatch it, and it was installed, and job is done. That's how sometime, simple it could be. For pylons, also tune mass dampers can be of great help. These are the readings of the significant steel tower, in which the bottom portion of the tower is cut. You can see how good the tune mass damper looks. You can also beautify the tune mass damper and make it look very nice, etc. But at times the client chooses to keep it very, very mechanical. Again, the containment type tune mass damper, it looks internally inside a container, which is put on tall stacks. If you closely see, you can see the mass vibrating left and right. Tune mass dampers, as I said in the beginning, are also used for long spanning bridges. These are famous bridge examples or structural examples where vibration was a real problem. I would like to
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
These are quite famous, and we all know that bridge, because of the vortex shedding effect, can be vulnerable to high amplitudes, and also for because of the pedestrian traffic. The bridges are usually, or the long spanning structures are usually very vulnerable. Again, this is how the tune mass damper looks for long spanning structures. Just one difference is that the motion of the damper is up and down, as against the tall structures tune mass damper, which happens to move left and right. And in this animation, understand how the damper on the above, if you see, the bridge is stable, silent, stagnant, and the bottom bridge is levitating. So so this is the tune mass damper, which helps the bridge keeps its motion into check. And because of the excitation that the damper receives from the bridge itself, it sets itself into motion up and down, and that's how it controls the overall oscillation of the bridge, and the comes to rest. So this is how a tune mass damper works for a long spanning bridge. This is a very famous example from India. This is Mumbai Trans Harbour Link Bridge in Mumbai, Asia's longest bridge. Happens to have more than 100 tune mass dampers inside the box of the bridge deck. It's a steel bridge. This is the very famous Millennium Bridge in London, in UK. This also has many tune mass dampers. Many such bridges around the world. This is a bridge in Norway, in China, in Hong Kong. So many examples of bridge, as well as footbridges, or long spanning floors, or cantilever overhangs, or staircases which have very long spans. All these kind of things which are long spanning can have issues with regards to vibrations and serviceability issues, comfort issues, etc. And tune mass dampers can really help stadiums as well. And bridge pylons are again an example of tall structures. But yeah, I mean, this is the Millennium Bridge. The day it was launched, the very same day it was closed for public because it was vibrating a lot. And it was closed for a good amount of time, many months. And then we were approached to design a solution for this bridge, and tune mass dampers were then designed. And after in fact, it was closed for 2 years. And then after the implementation of tune mass dampers, it was again open for general public. It is quite remarkable and famous in many ways. So floating floors, the very new topic of floating floor, happens to cater everything that is inside the building, any floor, any portion of the building, as we discussed in the beginning, such as helipad, swimming pools, some clean rooms, the data center labs, the acoustic rooms, the gyms, the dance studios, banquet halls, auditoriums, clubs, etc. All of these create a lot of vibrations and disturb the other parts of the building. So what you can do is again use a steel spring systems or a Novodam system. I will show you both, and I will directly show you how this system is implemented, so that you understand the concept of floating floor and how you can literally divide the vibrating floor with your main structure. So if you have already noticed, you essentially lay a layer of plastic film or a polythene sheet after installing the perimeter strip, and then lay the steel housings, which right now is having no springs, and you lay the new reinforcement, you lay the concrete over it, and then you put the springs inside the housing, as you can see it in the video. And after the springs are inserted inside the housing, in all the identified locations, you jack it up. So you jack the spring up and you jack the overall floor up. That's how you create some airspace in between the floating floor and the mother floor. So with this concept, you can create a floating floor which can vibrate, and the vibrations will not be percolating down. That's the idea of using steel spring systems for a floating floor. In similar way, of course, the execution is slightly simpler. You can also use closed cell polyurethane, the Novodam, but here you need not really jack it up. Just lay the the Novodam system, put the essential sacrificial shuttering or metal bars or ply boards or cementitious boards, etc. And then you can lay the new concrete over it. There are many simpler ways as well to make the floating floors. This is one of the ways. There are many other ways, very simplistic ways also, to lay the floating floor using polymer systems. Yeah, so these are some project examples. Again, these are some helipads which are isolated, as I have been telling. On the right hand side upper corner of your screen, the spring elements, it is covered by some PVC material, but inside there are helical springs, helical steel springs. On the bottom of your right hand corner, these are the closed cell polyurethane pads, which can be also used depending upon what kind of a frequency we are looking for. Similarly, for the swimming pools, again, the steel spring systems or the Novodam pads. These are some examples from all around the world. This is a gym or a fitness center where we have used the jack-up steel spring systems to create a floating floor. This is a banquet hall from Germany. Similar execution is done for Radisson Hotel in Noida, where in India, where jack-up steel spring systems are used for creating a floating floor for banquet hall. This is again a college auditorium, a theater in Pune, in Maharashtra, India, where such systems are used for a dance floor in Mumbai, for banquet hall. Here we have used something called as spring hangers to isolate all the hanging things in the ceiling, like the ducts, the cable trays, etc. inside a semiconductor facility. So many different kinds of hangers. Again, the hangers can be of steel or of Novodam. So if you see, many such hangers are put to hang the several duct work and cable tray work which goes into the semiconductor facility, or for that matter, any other building. Similarly, using Novodam spring systems for another semiconductor facility. This is for JP Morgan's office floor in Noida. Again, the Novodam systems to create the floating floor system. Anechoic chamber is quite a topic in India these days, where the cars are tested and crash tests happen. So anechoic chambers are also isolated. This is how we isolate the walls. If you want to isolate the walls, uh, you know, these are the isolators which are put for isolating the walls of the banquet halls. So this is done for JW Marriott. Now, this was all for buildings and structures. Now, a little bit about isolating the machines. So we know why it is important to isolate the machines. It is just not for the machine itself, but also to improve several effects of vibrations which can disturb the occupants in the building. Of course, primarily it is for protecting the machine and its foundation, to reduce the structure-borne noise or to increase the performance of the machine, to reduce the downtime, etc. But there are many other benefits of isolating the machine. Now, what essentially is the principle of vibration isolation when it comes to machine? The machine transmits some force. The machine will have some sort of an exciting force. And if you have an isolator underneath the machine, the isolator will absorb all the dynamic forces and absorb the exciting force, and the transmitted force will be nullified. I mean, you will not get any transmitted force. So basically, if you see it in the graph, the exciting force has a curve and it has some magnitude and some value, but in the transmitted force graph, if you see, it's quite a flat line. So all that is generated at the level of the machine is not really transmitted down. It is all absorbed by the isolator. So sometimes I say that for a dynamic system, you need a dynamic foundation. That's what we know as civil engineers and structural engineers. But with an isolator, you can have a static foundation for a dynamic equipment, because you can have an isolator which will take care of your dynamic requirements, and you can design your foundation just like you design your static foundation. So all different kinds of machines, again, whether it is boilers, pumps, compressors, generators, cooling towers, whatever, all can be isolated within a facility. Some examples to show you how the isolators look, how they are positioned, where they are positioned for blowers and pumps, for generators, These are done quite a lot these days I'm sure here as well in India. The hotel where I'm seeing, I saw the cooling tower was put on spring systems. So the similar mechanism for all the equipments, whether it is large fans or diesel engines or the larger generators, whether it is multiple isolating levels or single isolating level, all can be achieved in gas engines, in fans, in blowers, in pumps, in crushers, for piping systems, for engines, for presses, for printing presses, or whatever. I mean, any dynamic equipment inside a facility should be isolated if at all it is to be. And such helical steel spring systems can really help. Again, for a cooling tower, as I said, these are some isolator pictures. And the acceleration also, when measured at the top, it can give you very good result. When it comes to a small comparison between the three-dimensional system and a two-dimensional system, I mean, I need not go into it, but three-dimensional, as the name also suggests, gives you mitigation in all the three directions. So it is any which way is better, but it is also better in many other regards when it comes to taking care of uplift or levelings or, uh, bearing capacity, displacements, etc. So not just the three-dimensional benefit that you get with the 3D technology vis-a-vis the 2D technology, but also many other benefits like also replacement. If you see how this spring really moves, which may be of some interest to some of you, the spring literally can compress fully without achieving any blocking condition, simultaneously goes in the translational direction fully. And then comes back to its own position, the regular position. So that's the beauty of steel helical springs. Now, as I said, many different kinds of steel spring systems and many different kinds of the closed cell polymer systems. But these two systems are not just enough to provide all kinds of mitigations. Sometimes these systems need dampers, and this is how a damper looks. The pot damper, which we discussed in the beginning when I was showing you the base isolation systems. The pot damper essentially is a cylindrical pot which has a piston, a cylindrical piston inside it, and you have a viscous mass again, and the piston moves left, right, front, and back, up and down. That's how it protects the overrun and controls the oscillations in the building. Now, this is the effect of increased damping in such situations where the transmissibility reduces if you increase the damping. The orange line is with little bit of a higher damping as compared to the regular 5% damping. So the transmissibility reduces, meaning less and less will be transferred if you keep on increasing the damping. So that's the idea. Again, similar thing can be understood from the free vibration decay curve. These days, data centers and semiconductor facilities and high-end biotechnological facilities require something called as VC levels to be met. I don't know if this is the case in Sri Lanka as well, but many such cases are coming up around the world where such facilities need, because of their precision equipments, because of their high-end devices installed on the lab's floor, for example, the quantum systems, etc., you need the VC levels to be complied. What are VC levels? VC levels are the different vibration levels classified in terms of the velocity. And these levels are essentially very low level of vibrations, very minute level of vibrations. So for that, again, you need to have a filter. again, you need to have a spring system of a certain frequency that will take care of such vibrations and filter all of those out so that your system remains VC compliant. So these are again some installation images for you to understand how the system looks when it comes to complying the VC levels in such projects of semiconductors, data centers, etc. Any special protection also, if needed, with regards to vibrations can be done. On the right-hand corner, you see a small statue. It is called Statue of Nefertiti. It is in Berlin. So if it is very small and if the weight is very less, you can really isolate that. It's difficult, but you can. So that's all from the technical side from my end. A little bit about GERB. Uh, it it is globally present. It's about 120 years old now, and we have 5 state-of-the-art manufacturing facilities around the world. One happens to be very close to you. It is in Bangalore, in India, just a 1 hour flight from here. And the 4 other facilities that we have are in Germany, China, Brazil, and France. So these are our manufacturing facilities, and we are capable to just not supply alone the vibration isolators, but any kind of intervention if you need with regards to engineering, R&D, vibration assessment, etc. We can help. When it comes to installation and mounting of the system, we also provide installation supervision or installation in general for all our devices, apart from supplying, engineering, manufacturing, etc. So installation is also something that is taken care of. As I said, the company is about 120 years old. It was started in 1908 in Germany, in Berlin. And the India factory and the Indian operations is now about 35, 40 years old. We work in several different application areas, many of which we discussed. But as I said briefly in the middle of the presentation, you can also isolate the metro track or the rail track. So we also do that through our trackbed application, in which the track of the metro and track of the railway is isolated. The building isolation, tuned mass damper, seismic protection we discussed a little bit today. And we also take care of power plants and other types of plants where we talk about isolating the dynamic equipments, the large piping systems through our pipework system application and machineries, of course, we discussed, but then the large presses and hammers and things like that also we isolate through our metal forming business. We also try to take care of historical buildings and old depleted buildings by putting up the isolators underneath the column, which we call restoration of foundation. So, but this is something that requires a very high caliber workmanship. So this is something which is to be done here in India or in Sri Lanka. I am not sure if we have done something in this application area already. In ship structure, we talk about everything that is floating in the sea or water body, where we isolate anything and everything that is there inside or over the ship. In microseismic, we talk about the VC levels, which we briefly discussed. Micro vibrations, micro earthquake, primarily for data centers and semiconductor systems, biotechnological labs, etc. This is my final statement. Vibrations can be controlled wherever they occur. Thank you for your attention. I'm open for questions. You can note my name, number, and email ID. You can shoot your questions to me on email as well if you have any, and we can take the questions now as well. Thank you for the presentation.
This liquid, viscous that what is the liquid that you use?
So the formulation is proprietary to GERB, but primarily the viscous mass are of two types. One viscous mass is bitumen based, which is used for certain kind of applications. Another viscous mass that we use is based off silicon, and that is used for the high-end applications. But it is not bitumen or silicon alone. There is a formulation that goes in, and of course, for every situation, every project, it is customized, and the formulation is decided, tested, quantified in terms of damping resistance and other parameters, and then used in the design model in terms of the properties of the damper, and then the damping percentage is established basis those properties. Essentially bitumen and silicon, but there are other things as well.
You are true that you are paying also as that.
We in GERB we don't use rubber at all. We are a rubber-free company. We use only if at all we are using anything which is polymer, we are using closed cell polyurethane, which is Novodamp, but not as a damper, which is used as a spring.
That's probably last long.
Yeah, it
The problem is sometimes.
yeah. So as Professor Mendes, just mentioned in one sentence, yes, you are 100% right. Neoprene or whatever rubber becomes brittle after some time, and you really need to change it after a couple of years, and the durability is very less. It's not really a suitable material for vibration isolation. It may be good for insulation, but for isolation and vibration isolation, certainly not. Closed cell polyurethane displays a very, very good and long life. And as it is closed cell, it is inert to water, ozone, chemical, oil, air, or any other foreign element. So automatically the life increases multiple fold. Bridge bearings are essentially neoprene rubber, and as it is neoprene rubber, usually after a few years these are changed. That's a challenge in the bearing industry. We don't make bearings.
20 years, 10, 20, some.
Yeah, we have something for that, but you really cannot compare in terms of cost when you are comparing such technology with something like rubber. So usually we say that we don't have anything, but essentially, if you look into it, the base control system that we have can be used. And we have done some projects in Russia where spring systems along with viscous spot dampers are used as bearings for bridges. And we are also trying to use now our polymer systems, the Novodamp systems, the closed cell polyurethane as bridge bearings, integrating these systems with steel plates like LRBs for bridge bearings and even for buildings. Yeah, essentially, bridge bearings means rubber, which we don't do.
Yeah, the question we had was, we were just discussing, you had a graph of the very high versus dam.
Yes.
I think that's based on Tamura's work.
Yes.
Tamura's. Yeah, that's something that is really some debate as well, where we say sometimes the displacement of a building increases. We say the damping could change.
Yes.
Increase. At the same time, Tamura's work is showing is going down. No, the graph we show that it's. So any work can be done to measure, that graph.
Yes.
Based on Tamura's work.
Yes.
But it's so is it any work being done on that measurement? So
Yes. In fact, I myself have measured a building. In fact, couple of buildings, some 4 or 5 buildings. But the one which was really dangerous was in Gurgaon. I will, of course, not take the name of the building, but it happens to be of one of the most, not one of the most, probably the most powerful man in the world. So you can guess the name, but yeah, I mean, that building in Gurgaon, when I measured, we registered a damping of about 1.1%. And the assumed damping for wind tunnel and for the analytical calculations was 2%. Now, why we did the measurement at all? Because we were invited to check what is really happening. And what was happening was the building was swaying left, right, front, and back. It was swaying very badly. Why it was swaying? Because actually in the building, the damping was not 2%, but very less, 1.1%, which had shot up the acceleration multiple fold. That's the reason we say that, when you are near completion, get the damping checked. Of course, you can get the frequency checked and post-process and get the damping out of it. But when you get the damping checked, you can at least validate and correlate it with your assumed damping values from your analytical model. And if it happens to be not close enough, you can do something about it. But you cannot really all the time put tune mass damper on the top, because tune mass damper will be of some weight, but you have not considered any weight during your analysis. That's why I said during analysis, it hardly takes anything to add 1 or 2% extra weight as a contingency weight on the top of the building, thinking that if anything goes wrong, I will add a TMD at the top.
How do you check the wheel?
So the ambient condition is good enough. We have high-end DAQ boxes and acceleration devices. Yeah, it's all possible.
No, but
You really need not.
Because
Yeah, it's enough.
so our experience is fact. But we had two water tanks that provided the damping and
Yeah.
the tune mass per design.
Yeah,
But when we measured the damping, it was enough, so we didn't have to do mass damps. That's a good approach, what you're saying.
yeah,
But we did with that grade.
yeah. So
Because I thought the wind was good enough to.
I think it also depends on the efficacy of the machine. If you can really catch the low frequencies, because essentially the buildings will be having very low frequency. So at 40,
When you captured that.
Yeah.
That was enough.
or in all the cases actually, in the ambient condition, so the building was essentially swaying. I mean, you can see from your naked eye directly. What is there to excite it all?
Yes. So we got the lowest top.
Yeah.
Also.
Yeah.
Now we are the most. Some accelerated. So I know that's a good part. So coming to this graph, so about the height, we don't know because that, there's some debate. I was initially thinking that the displacement increases the damping. That's what I learned from Bill Melvin, which I wrote. But Tamura's work is showing clearly it's going down.
Yeah. And I mean, it is something which,
This is all right, but other part.
which one?
Yeah, this one is.
This one.
That,
Yes. I may ask the question again.
I don't know, this is showing that the height increases.
Yes.
That's what we're just discussing. Damping reduces.
It's,
Tamura's measured, I know.
Yeah. so, I mean, it is something which is registered. It's not about if the height is, I mean, my understanding is this, Professor Mendes, that the graph is not about if the height is increasing, the damping is reduced. This graph is to essentially ascertain that damping is not always what you have assumed.
But that is true. Yeah, this can be different buildings.
Yes.
Different types of.
Yes. So many factors.
Which one? Your water's concrete or steel?
Concrete, all concrete.
So the reason I'm saying higher damping or always frequency is because higher displacements, building can be cracked a bit more.
Yes.
So that is really giving that energy absorption more.
Yes.
So this is my argument, but I don't know how you measure all this, but maybe different buildings.
Other thing is like, so there is you have the, so how, yes, we have some shear connector, right?
You're talking about viscous wall damper?
whatever that you have in the soft base and the structure that you are looking at. But there is shear connector between in case of a frequency.
You're talking about base isolation.
Basically,
So a very interesting fact is this, that for base control system, the base isolation system that I showed you, in most of the projects you have bolts which are connecting the upper body of the isolator with the building and the lower body of the isolator with the pedestal column or foundation or whatever. But you don't need it. Why you don't need it is because we put something called as resilient pad or an adhesive pad on top of the isolator and the bottom of the isolator. Now this resilient pad has very good properties in terms of catering the shear forces. Now if you see whatever shear forces will be generated because of earthquake, whether it is 20, 30, 40%, whatever. Now the friction coefficient of the resilient pad is quite high, sufficiently high enough to take care of any shear forces or anything of that sort. Uplift any which way is not there because the dead load is so high.
yeah.
So all things are taken care of, but usually consultants would like some connection. So we put the bolts, but it is not needed.
But so hole between, but you don't have the hole between the.
No. In some photographs, if you have seen the bolts, that is transportation bolt, which are essentially removed after the installation is completed.
Today you are showing mostly the other way around. You are isolating the machines, so from the flow.
Yeah.
So, earthquake is other way around. So, yeah, isolating the flow from the earthquake. From foundations.
Okay. But it says is involved with that is being here
Because of the,
get
because of
the
friction.
Now, if you see this, there is no, there is bolt here, but if you don't want to put the bolts, we can remove the bolts. You don't need the bolts. Bolts are just put to give some comfort. Yes, that's enough.
What is the word you talked about? Sorry. What you were talking about something? Easy or something like that. What do you want?
So this is the, so the construction is like this. You have this bottom yellow portion.
Yeah.
This is the bottom body. Bottom housing, bottom cabinet. On that cabinet, you have several springs put inside guides. Okay, you have the springs, and then you have a top body which is very similar to the bottom body. Again, it has guides, but it is covered from the top. It is put from the top, and then the building continues.
Bring it up.
Yeah, it's pre-stressed, so you release it later. But these bolts that you're seeing here, maybe I'll have some photographs in which there are no bolts. Like you see here, there are bolts, right? But if you see here, there are no bolts. So, I mean, bolts are optional. If we want to put bolts for some extra comfort or whatever, we can put the bolts. But then if you're using the bolts, the force flow path will be from the bolts because bolts comes in the critical path. But if you're not putting the bolts, essentially the resilient pads will take care of the forces.
What is this? It's just like made out of what?
Resilient pads are again made out of a composition of material which is essentially bitumen and silicon. Yeah. And there are some perforated layers. When the load comes, it is otherwise sitting idle in ambient conditions. But when the load is applied, because of the heat, this composition flows out of the perforated layer and makes a bond between the isolator and the concrete.
These pads The goal is complete that of by itself. That's all there.
Nothing. I mean, these pads are, so these pads any which ways will not be exposed outside of the plan of the isolator.
See, so
It will not be exposed because it will be within the, periphery of the isolator. It will not be seen. You will not be able to see the pads. Only, let's say, the edges of the pad probably somebody can see, but then essentially nothing is exposed out.
So this pre-stress, without braces, the shear will not work. We need to have the vertical force. So if there's vertical acceleration, then would that affect the force that we put in?
No, the vertical for the work.
Discuss the what can it happen? Because the friction depends on the vertical force.
Yes. So, if I got your question correctly, yes, the friction depends on the vertical force, and we pre-stress and we put the springs inside.
I'm talking about vertical acceleration. Then effect on vertical acceleration.
Yeah.
What we say is the
Yeah.
balance work.
Yeah, we just balance, but weight depends on weight difference.
Yeah, so the vertical force, I mean, if it is for the earthquake that we are talking, the vertical force will be taken care of by the vertical stiffness of the spring. So it will be absorbed there itself. So the upper portion of the spring, which is connected with the floor, which has the resilient pad, will not be experiencing that force at all.
It's not only lateral, but vertical.
The vertical as well. And in this video, if you see, here, so the force is not getting transferred at the top any which way. Yeah.
In this one, there's no vertical acceleration, looks like only horizontal.
No, there is vertical. There is vertical. Yeah, I mean, it is going left and right, but if you carefully see, the spring is getting compressed in the vertical direction as well. Yeah.
It can start with here.
So, base isolation is usually done for buildings which are governed by earthquake load cases or by load cases of vibrations coming from anything outside. But if it is wind, primarily the wind load case will not be governing these kind of buildings. If it is a tall building, you would not go for a base isolation, but for a tuned mass dam. In which you can, and of course
especially Myanmar, there is cyclone and earthquake at the same.
Yeah, so tuned mass damper actually caters to a particular frequency. Now, for earthquake, it is a little bit of a challenge if you are catering only to one frequency and try to, with full confidence say that you will be mitigating the earthquake. That's a bit of a challenge. So it is primarily done for wind. At the same time, it can be tuned to take care of earthquake for certain frequencies. Let me put it this way.
So Taipai 101 no by this section.
Taipai 101, there is a big mass on top, which is a tuned mass damper. And recently, when there was an earthquake, many people started congratulating on LinkedIn saying that, the damper has protected the structure from earthquake, etc. But this is not true. It is for wind. It is not for earthquake. It happened so that the frequency of the earthquake near matched the frequency of the damper, and it happened to help. It was just a coincidence. And it is not designed for earthquake.
Because the earthquakes that happens ground-wide.
Yes.
Wind is not only at the
Yes.
ground. So
But for whatever motions, you can design the tuned mass damper for certain frequencies. Like the Burj Al Arab project, you have 11 tuned mass dampers catering to different modes. In earthquake, you really cannot cater to one or two modes. It can be for different modes that the building becomes vulnerable.
How a meeting like cantilever. Well, it's some work here.
Okay. In Colombo, one, I think TMDs.
Stable light.
Similar to those languages.
That was the.
Mhm.
So they found the natural frequency and use the
Yeah,
made to.
yeah, that's the way it's done.
20%.
That is the reason.
Yeah, that was. But that's very good.
Very good. Any question from the questions?
Yes, we have the questions. The live chat, but before that,
Weight.
Weight of?
This time more than.
So, I mean, if you're talking about the weight of the tune mass damper, it does not matter, but I mean, just to give you an answer, the weight of the base isolator could be from 1 kg and it can go up to, let's say, 1,000 tons. Yeah, because it depends completely on what you're isolating. If you're isolating a very small thing, you really need a very small isolator. And if you're isolating a giant building, like we isolate a lot of defense buildings for a load of 30 G for shock. Yesterday in the conference we were talking. So we isolate buildings for shock as well. 30. So for that, the isolators will be very big. It is nothing special. The spring will have a bigger coil, the dia will be big, and that's all. It's like a building. What can be the weight of the building? It can be very small and it can be very huge. Depends on just like that, So there is no as such domain of weight. Can be anything. Yeah, I mean, weight matters in particularly your case where you are floating the city or whatever. So for that, of course, I mean, it will be very less, depending upon
Whether you have like a sheet, like whether we can.
polymer.
Yeah, polymer.
Yeah.
So that we can, where the weight is a big problem.
Yeah, so it depends on what are we trying to do with the isolator. If your use case is to, take care of the spectral accelerations because of the waves, is that the case? Yeah. So for that, and what are we trying to isolate here? Building. And what will be the weight of the building?
Speed.
Yeah. So I mean that can be managed because it is done in power barges, right? All different kinds of equipments are put inside the floating ship, which is like a power plant. And you have engines, DGs, fans, coolers, motors, pumps, whatever. Everything is put on the isolator and the accelerations are taken care. It's quite common. So now, but the interesting fact is that you're trying to float a building, which I am very eager to understand in deep detail after this. Yes, we can take the questions, ma'am.
yes, we have the Google form for the attendance open now, and it has been posted in the YouTube live chat and as well as the YouTube live description. So please go ahead and mark your attendance if you wish to register for the certificates. And please note that the Google form will be only open for 20 more minutes. So hurry up and mark your attendance before the Google form closes. And with that, we can move on to the questions from the live chat. There's one question, sir. Do seismic isolators require regular maintenance or repairs over time? And repairs over time. That's
Okay. So all the isolators or all the devices that we saw in the presentation are all passive in nature. When I say passive in nature, that means these isolators are not interfering in the regular load cycle of the building throughout its life. It is just resting. It is just sitting like a dead element in the project. and there is no exchange happening. There are no seals, there are no valves, there is no orifice, there is no pressurized element in any of the things that I showed. So essentially, there is no operation happening with the isolator. So no maintenance is required. No, as such, nothing is to be done. In fact, we call it fix and forget system. However, if you really want to again go and see and check or whatever, of course, there can be some foreign ingress, something that is, disturbing the isolator or whatever. You can check once in a while, but as such, on its own, isolator does not need any maintenance until and unless it is in industrial projects where it is in completely, greasy environment, a heavy press operating on top of the isolator, there is oil flowing around the isolator, then you need to maintain. But in all other cases, specifically in buildings and structures and regular machines, no maintenance.
So this, with respect to the this material, so there is no, time, yes, fatigue.
Okay, so with regards to durability, fatigue, with regards to failure, with regards to service life of the isolators, I'll just give you a quick anecdote. Few decades back, in one of the power plants, they wanted to buy new isolators for the turbine. Their old turbine was sitting on our isolators, and they wanted new new set of isolators for the new turbine building. But GERB being GERB, we advised them that you don't really need to buy new isolators because your old isolators are good enough. We have checked and you can use the same isolators. But the client said that we cannot afford a downtime. So we will be putting the new turbine, we will be putting the old turbine in the new building simultaneously. So we want you to give us the new isolators so that we don't waste any time. We put the turbine directly, taking it out from the old turbine building to the new turbine building. But we still insisted that we can do it very quickly. We can shift the isolators. You really don't need to purchase new isolators, etc. They got a little agitated and said, if you are so confident, why don't you buy back the isolators? We bought the isolators back. We were in benefit because we bought it for the previous price. So we bought the isolators back and used it in another project. Simple. Because there is nothing happening, to the isolators, to the viscous mass, or even to the Nova dam. Nothing happens. It is just there. Because these isolators are, whether it is Novodamp or helical steel spring systems or the damper, as I said, is not doing anything. Is just there to take care of the load, and it is passive in nature. Usually, many isolators or many things that we know are interacting all the time in terms of having some absorption, some shock, some exchange, some pressurized element, but nothing is there here. So no maintenance, no life issues. In fact, the age of the Novodam calculated as per lab is 700 years, which nobody knows. But then even if it displays half of it, is very good enough. So that's the kind of confidence we have in these isolators that, no durability issues at all. Yes. Yeah. In power barges, you mean? Yeah. One more aspect to durability, just as Professor Mendes mentioned, marine. I got reminded of one particular thing, that in marine environment also, you just need a different kind of coating on the isolators, which we have done, and we have given a 100-year guarantee, for the for some bridges in which the dampers are put in marine environment, very, very toxic and high salty marine kind of an environment. Nothing happens. In marine projects, where usually in large ships, called power barges. Captive power plants are set up, small power plants are set up. And the ship floats, generating energy and using or whatever, maybe not my subject, but then these ships or power barges houses a lot of different equipments inside it. As I said, whether it is a stack, whether it is turbine, generator, engines, pumps, motors, fans, blowers, etc., etc. And all of this becomes very susceptible and vulnerable to vibrations because the waves, the high tides and the low tides in the water body creates sudden levels of accelerations which are beyond the allowable limits of the machine. So you can put the isolator and treat these vibrations just like earthquake in terms of your analysis and control the vibrations, reduce the vibrations which are trying to go inside, filter out the energy of the vibrations using these isolators and damper systems. Simple.
So the earthquakes are dominated by the lateral accelerators.
Yes,
But in this case, it's a combination.
it's a combination.
So it's nothing.
Nothing, because in earthquake also we take care of vertical, and more than earthquake, when we talk about, metro vibrations and rail vibrations, the dominant vibration is not lateral but vertical.
Yes.
So we take care of the vertical vibrations invariably anyway. That is why for earthquake, usually clients try to use base isolation systems which are famous in Australia and New Zealand.
Not in.
In New Zealand, LRB, the lead rubber bearing systems, which are translational in nature, left, right, front, and back, not vertical. Because vertical is not a big business in earthquake domain, but these days it is. Codes are getting revised, the vertical,
Adding some.
the vertical components are a big.
Sometimes on vertical. That's okay.
But most of the codes are getting revised now. Vertical component is also a topic now. So our isolator in any way takes care of the vertical vibrations. So that's how we are able to solve the vibration issues of buildings which are close to metro and railway projects, railway trains, because the vibrations have a very good component of vertical oscillations as well.
Yes.
For bridges, we in the section of the bridge, let's say if the first mode and the absolute center of the bridge has large levitations, large oscillations, we can put the tune mass damper there and take care of it. You just need to bolt the frame on which the damper will be put. If you see this, so this is the TMD. Now the TMD is supported on this frame, which is transparent, just for this animation. And this frame is to be connected to the bridge so that, it can become part of the bridge. Like a floor vibration or bridge vibrations. So sometimes for tune mass damper, you need some connection because you want to hang the tune mass damper through a frame, and that frame essentially needs to be connected to the building to become sort of monolithic with the building. For tune mass dampers. For base isolation, you don't need to have a bolting connection. You have a connection in a different way. For viscous wall damper, again, you need to connect the damper from the beam, bottom of the top beam and top of the bottom beam.
There's one more question regarding the seismic isolators again. Are there any common failure modes associated with these isolators?
Yeah, so that's since we are sitting in Colombo, I think that's Muthaiya Muralidharan's question. A dusra kind of a question. I don't know what is the failure mode of my isolator, you know? I mean, there is no failure mode as such, but because the isolators are in a way good enough to take care of the loads in all the ways. If anything happens with regards to, a failure situation, one should be careful about the load capacity of the isolator, which during design we take care of the load capacity invariably. And then the isolator also has something called as block load, which is 200% of the capacity of the isolator. So for the failure of the isolator, it really needs to have something which has gone wrong in a very, very big way. The load has to cross 200% the limit of the, designated load capacity of the isolator. That could be one of the failure modes.
Basically, what he's asking is, did it fall down?
No, that's what I explained, that the capacity of the isolator is quite huge. The nominal capacity that we claim to the customer is just the nominal capacity. There is something called as block load or block capacity, which is 200% time more, 2 or 3 times more than the nominal capacity. So nothing happens. No failure.
So there is no failure in your.
So, yeah, I mean, failure has happened, but the failure that has happened when there is some foreign ingress. As I said, if the isolator is put in a greasy environment, in an oily environment under a press, it was supposed to be cleaned every 6 months, let's say, and the auto company has not cleaned the hammer and the isolator for 2 or 3 years, then the spring has really, because something will go inside the helical structure of the spring and then blocks everything, slowly. So that all those things have happened. But essentially, for example, GERB happens to be a 120-year-old company, and we and our isolators are in practice and in position since last 60, 70, 80 years. So there are substantial, testimonies and evidence available in the world that nothing really happens. That's the beauty of it. And it is, you will get it from this. It is high quality steel, and just not steel. Again, it has, let's say, a little bit of nickel, a little bit of molybdenum, a little bit of chromium, and a few other things. So the quality of steel is also improved multiple fold. Now, when there is a steel structure standing for 100 years, why can't an isolator, which is improved version of that steel, stand for more than 100 years? It definitely can.
So that means that you don't need innovation.
We keep innovating in many, many ways. As I said, I mean, for bridge bearings and for building isolators, for different, even for the same applications, the Novodamp or the closed cell polymer, along with steel plates, to take care of more loads and to optimize the isolation in a way using polymer instead of steel plates, which are in trend now. So we, of course, we have a very, since you talked about innovation, we have a very elaborate team in Berlin. I was fortunate to visit Berlin many, many times now. And when the first time I visited, I was literally shocked to see so many professors, very experienced guys, all PhDs, researching on all these topics since 1990 to 1991, writing codes and doing things when in our parts of the world we were not having computers. So that's the legacy of the German technology and GERB, that innovation is really the key. And we have a very big R&D facility in Berlin. And many of the things that you see are, for example, I'll tell you, in tuned mass dampers, we are using something called as eddy current tuned mass dampers in some projects these days. For example, we are using something called as magnetic field tuned mass dampers in some projects. In one project, we have used a tuned mass damper which is not visible, but the facade of the building itself is tuned mass damper and oscillates and protects the building from earth. So those kind of innovations are there. What I show you is usually the technology, the regular basic technology, which we primarily use in regular projects in our parts of the world. But of course, different projects needs different innovations. So we definitely are open to that and we do that.
These buildings in India as well.
Yes,
Not in-
yes. One I showed you in my
Oh, that's
example.
it.
Yeah, but many,
Most of the towers are.
yeah, many in India, many. These days you can visit, let's say, any big city of India and you will find one
Yeah,
big
not
project
towards
of
the south.
towards the south as well.
No.
Not for earthquake, not for
Not
earthquake.
the-
Not for earthquake, but for metro vibrations
Metro vibration.
or for
No,
industry.
metro vibrations can be anywhere.
Yeah,
We
yeah,
also have a, I mean, we are actually having a project to have hotels over the railway.
yes, yes.
So when, that's what you want, according to what I think you said, but you think it's better to isolate the
Oh, yeah, it is.
track than the.
Yeah, it is. If it is metro project, it
It's
is
not a metro, it's
so-
normal,
a normal railway. So in the sphere of vibration, there is a saying called, it is always better to isolate the vibration at the source. But if for some reason you are not able to guarantee the isolation of the vibration at the source for any reason, or for its entire life, or the efficacy part of it, as I showed you the SHREM project, of course, the Mumbai Metro Rail authorities will be isolating the track. We only will be doing it. We also advise the client that you really don't need isolator here because we will be isolating the track. But how do you guarantee, how as an owner of that hotel, you take that, confidence that somebody else will take care of all the vibrations and you need not do anything. So that does not happen. So it's always good that high-end facilities are isolated if it is close to railway or metro systems. In fact, if it is over the railway or a metro system, definitely it should be isolated. There are some projects in India which in Nagpur, we have isolated the full building, which is called 0 Mile Station. It is a building on the station. Entire building we have isolated.
Yeah,
and put
it's a problem. So talk about in Melbourne, there's a now new metro tower, we have station now, university. So there's our medical cancer facility, hospital. There are so many equipment, so medical equipment are worst in terms of the sensitivity. So
Yeah,
track is isolated, but it's
Yeah.
not enough. So
Yeah.
this was a problem. So
yeah,
it was closed, could open for some time. At that time, when the cancer building was, they were building it, we went and measured as well.
Yeah.
Our department, a couple of people of us. But at that time, this was equipment, but now we don't want to take responsibility, but yeah, so that was a problem. So
Yeah.
now the train has to go slow around that.
Oh,
Yeah, because I don't think that's medical equipment is so sensitive.
no, but what we can do is, for the metro, for the sensitive equipments, we can make a floating floor, which should be having a very low frequency, good enough to filter out all the energies which are in the lower frequency range also. Yeah, for example, Mendes sir, if we put, let's say, a 1.5 hertz solution for the floating floor, 1.5 hertz solution, probably studying the resonance, of course, probably entire frequency band will be filtered out. So whatever energy you have can be filtered out. Similar is the case for semiconductor labs. India's first quantum system, first supercomputer. We are isolating that. So that can be done.
But that's also another very sensitive.
Yeah, that's why I'm saying it is even more sensitive.
More sensitive.
So if you see this, this is the most sensitive vibration levels that one can see. You know, see, these are, of course, VC graphs, you know it, but VCC, VCD, VCE levels, which are so small, 12.5 micrometer per second, 3.1 micrometer per second, meaning any vibration beyond, let's say, 3.1 micrometer per second should not transfer and disturb the equipment, because the equipment is sensitive enough to be disturbed by any vibration which is over this value. And that is how you comply with VCE levels. We are doing that.
Got a very good point. There's a center being there close to a line and we have.
Yeah. In Australia, we have put tune mass damper for a project called Quay Tower. Yeah.
Oh, no,
They got so many awards. It
Yeah.
was done by someone known to us,
Yeah.
BGND. So it was so with the one we got awards as well in Singapore, we have a lot of stuff, we also got a lot of awards.
It's quite famous. We did tune mass
For the
damper.
building, but that is called a response factor. That's all.
Response spectrum.
Response factor.
Response factor.
So we make sure that, we know that response factor.
Yeah.
Yes,
In terms of acceleration?
that's right.
Yeah.
So we dancing towards that higher.
Yes. Yes.
That's all.
So,
Floor vibrations. Yeah.
no.
These are yes.
Yeah.
Yes.
Coming through the.
Yes. This is for the floor.
No vibration, but that's vibration from people. Vibration is passing from the other.
Yeah. This even, I mean, people walking
Also
can disturb the readings in the machine.
Both.
So yeah. I mean, this happens to be very sensitive, and the vibration spectrum is to be studied, and you just need to position the isolator for a particular right frequency, avoiding resonance and filtering out all the high bands of energy in any frequency domain. That's
It's like that is more how people feel the vibrations.
Yeah.
Yeah, it's a machine speed.
yes, absolutely right.
We
Absolutely.
had a dancing floor, below we have a roof.
Hmm. Yeah. So we isolated Radisson Hotel's dancing floor. They had exactly the same issue. They could not let out the rooms underneath. Who will, pay that much money for complete disturbance all the time? So just the new floating floor, and that's all done.
The sound. So, roof structure, it was by the
Sound off.
sound of the we were having a art.
Fine. So, okay, so there is, of course, with permission of Professor Mendes, I am going into these directions where, he is the giant expert. I know nothing, but still I'll make my points. So there are two things, Shiromal sir. One is ground-borne or structure-borne vibration and noise. And the other thing is airborne vibration and noise. With isolators, you can cater to ground-borne vibration and noise. Structure-borne vibration and noise, you cannot. But airborne vibration, did I say it correctly? Airborne vibration and noise, you cannot. But airborne vibration and noise is made of or constitutes two things. One, it gets established, or airborne vibration and noise generates let's say, partially from structure-borne vibration and noise, and partly on its own. So when you are taking care of structure-borne vibration and noise already, structure-borne vibration and noise, you are already taking care. Simultaneously, you are also taking care of airborne vibration and noise partly. And partly it is to be taken care of by acoustic treatment. That is how you do it. So in India, these days, for such situations, what you are doing is you are putting a floating floor. Essentially not with steel strings, because it is expensive. You don't need Mercedes all the time. Sometimes, Hyundai is good enough. So polymer systems are put, and then you isolate the floor, and then you isolate the ceiling as well. So you make something called as box in box or room in room. So everything is isolated. Now structure-borne vibration and noise is taken care of. And airborne vibration and noise is partly taken care of. And partly for airborne vibration and noise, you put the acoustic panels and other things, and you take care of everything in that manner. It is done like it's an everyday thing. It's happening like in every.
The main problem was we have all seen it, this is good. Due to this vibration, the fireproofing.
Yeah, false start. So the
only solution was to that the fireproofing. Or that's the part of fireproofing by other. There is no
No.
the detail for.
But again, I mean, it's better to take care of the vibration and noise than to how many times you will. And of course, that way you cannot control the vibration and noise. You are just essentially taking care of fireproofing material again and again.
That's now there's how many people actually heights.
Yeah.
So good stuff. Depends on the singer as well.
Yeah, all kinds of, as I said, I mean, in my last slide, this is something that I am not saying, but the company says vibrations can be controlled wherever they occur.
So the source is a
It's better. It's better. It's better.
Any more questions or? That's anyone the question.
Maybe a alien topic for students. It will be. I tried to make it a little bit video oriented, picture oriented, but I'm sure for that matter, anybody cannot make it as interesting as a game of cricket between India and Sri Lanka. But yeah, it was, I suppose, not. No? What? These days. That is just these days. That is just these days. But I think maybe when I was a kid. No. I remember. In fact, I can list down all the 11 players of Sri Lanka when I was a kid, and I used to watch cricket. All the 11 players I can mention right now. I mean, in India, Sri Lankan cricket team and West Indian cricket team, they are liked a lot. People like them a lot.
Shall we conclude and
Yes, please.
Get conclude the webinar first? Because we like to talk about cricket a lot more.
Sure.
Thank you. Today, thank you very much for coming all the way here. And also with such a, in fact, again, Pratik, coming right now, you just came from Colombo and listening to us yesterday, and also coming to the office and giving this valuable webinar. Your company, we have heard, of course, coming from Berlin, and you have I think more than 100-year history in that company that we all have heard in different places. But to really present in a very simple way all that equipment and also your understanding of the fundamentals, rather than just like someone talking about some equipment or something is different. So, but you gave the fundamentals as well, which really made it very useful even for us. That there were certain questions, and you saw the vibrant discussion, not just a vibrant discussion about the vibrations. And I think that which you saw, we could have gone and on for those questions, and yeah, we all had a number of questions that you really answered, gave the answers. And then this is also we learned today that it covers all sorts of systems. It really caters for many things. So also we have a young, very good audience here as well. And yeah, thank you also, and thank for everyone being here. And also there was a online audience, which we also saw the numbers of people were listening online, even with short notice there. So we want to really thank you very much, and not only welcoming to Colombo, but really to our office.
Pleasure.
And that's really been, thank you very much. And I'm thanking on behalf of Mr. Shomal and our team here, and also had to thank the organizing team always under Chatmi's directions, and Shan is here, and everyone joining us. Thank you very much.
Thank you. Thank you so much. It was a pleasure. Thank you.
Thank you very much.
In this case, we avoid talking.
Shall we conclude the webinar? Just small notice, yeah. Yes. Thank you, Mr. Pratik, again for such a informative session on this seismic isolators and vibration isolation systems, seismic protection systems. I think it was a topic that was kind of new to some of the engineers, but also a lot of information was shared, and I think the knowledge was shared among the engineers, and thank you for that. It was a very effective session with all the graphics and everything. We could understand a lot with that, and I hope all the participants have registered for the e-certificates as well. If you have faced any issues with the Google form, you can take a screenshot and then send us through our WhatsApp or email, so we could help you with that. And also thank you, Mr. Pratik, for the Q&A session, for clarifying all the questions from the participants, from the audience, and from the online participants as well. And with that, we can conclude the session, and we have 2 courses scheduled to start, and registrations are open for the AutoCAD course, and also yes, let me share the screen first. The AutoCAD and SAP 2000 course registrations are open, and you can find the registration links on our social media. So you can go ahead and register for the courses. And if you want more information on SDI webinars, courses, or any other workshops that we are carrying out, you can always contact us through our WhatsApp, email, LinkedIn, and Facebook social media platforms. And until we come with another webinar for you, have a nice week, and have a nice day. Thank you everyone for joining.